Derivatives without exponents. And that's our topic for today. And we have this. I think you'll remember a lot of this as I go through this with you. We had done an in-depth discussion of derivatives back in some previous videos, and I hope you followed along, because now we're going to go into the juicy stuff here. Do you remember the equation S equals 16t squared? Okay. What we're going to do is we're going to replace the t here with some numeric value. And this, in this case, S is going to represent the distance that a particular object has traveled. When we're talking about this particular object, we're talking about taking a golf ball and slinging it down some multi-story building. Okay, we go up several flights of steps on this building, we take a golf ball, we suddenly drop it and hope it doesn't hit somebody in the head when it hits the ground. Okay, and that t represents the number of seconds that elapse from the time you drop the ball until it actually hits the ground. Okay? All right. Now, we're going to replace this t with some kind of a numeric value. Now, we do not know what that numeric value is at this point. So, we're going to call that numeric value x1. Now, this x1 will represent the number of seconds that the ball has dropped since you let it loose from the top of the building. And it doesn't matter whether it's 4 seconds, 5 seconds, 8 seconds, doesn't matter. Okay? Now, delta x here is going to represent the number of seconds that it continues to travel after it reaches that whatever point. Okay? So, let's say the ball has traveled 5 seconds already. This delta x could represent another second, which would make 5 seconds plus 1 second equals 6 seconds. Okay? So on and so forth. Now, if the ball drops an additional second or half second or 2 seconds or whatever many seconds it drops, then it's also going to drop a certain number of distance here. Okay, so this is the distance it's going to continue to travel down. Now, it's traveled so many number of feet already, whether it be 400 feet, 500 feet, 800 feet, doesn't matter. It's already traveled a certain number of feet down. This delta S is the representation of how many feet it's dropped after it dropped from this point. Okay? So, this could be 400 feet, and this could be another 100 feet, which 400 feet plus 100 feet would be 500 feet. Okay? Now, as we know, when we have something like this, we're going to factor it out. And this is how we factor it out here. We have x1 squared plus 2x1 delta x plus delta x squared. Alright? And we're going to take each one of these terms times the number 16. And when we do, we get s plus delta s equaling 16x1 squared plus 32x1 delta x plus 16 delta x squared. Alright, now what we're going to do is we're going to remove from this equation the original, say, 400 feet that the ball has already dropped. We're going to remove that. We're also going to remove the number of seconds that the ball has already dropped, say 5 seconds or 6 seconds or whatever. So this term disappears, and what we have left is delta S equaling 32 x1 delta x plus 16 delta x squared. Alright. Now we're going to divide both sides of this equation by delta x, which is going to leave us with 32x1 plus 16 delta x here. Alright. Now we know that we can't change that delta x to 0, because if we do, then we're dividing this by nothing. And that's absurd. Okay? But we're going to suppose it is possible. We're going to say, hypothetically speaking, it is possible to replace that x with 0. If that be true, then delta S equals 32x1. Okay? So that x1 there is a number with a t-shirt on. Well, the thing is, we're going to cover that number with a t-shirt on with another t-shirt. So now we can say that delta S equals 32x. The x representing the x1 here. And that x1, of course, representing some numeric value. Okay. Hopefully I didn't confuse you too much. Now, if you'll remember from a previous video, I had y equals ax squared. So, anytime you're trying to define the derivative of y equals ax squared, you're going to get delta y, which equals 2ax. Alright? And we can prove this out. It wouldn't be that hard, but I'm going to let you prove that out for yourself. Make a video response of your proof and send it to me, and I will gladly include it on my future videos. I may at some point prove it out to you, but we need to continue our discussion here. Let's just suppose that there was no superscript up here on the t. We have an equation now of s equals 32t, as you can plainly see right here. Alright, so now we have s plus delta s. Again, s representing a certain number of distance that the ball has already dropped, delta s representing the distance that it continues to drop thereafter. Then we have this number 32. We have an initial value. This is the number of seconds the ball has dropped thus far. Say 4 seconds, 5 seconds, doesn't matter. Delta x will represent the number of seconds that the ball continues to drop after the 5th second, after the 6th second, so on and so forth. So we got s plus delta s equaling 32x1 plus 32x. Okay? We're going to remove the original value. Say we had the ball already dropped 400 feet. We're going to remove that now. And we said that the ball dropped a certain number of seconds already, so we're going to remove that term out there, which leaves delta s equaling 32 delta x. And so, if you divide both sides of this equation by delta x, then delta s divided by delta x equals 32. Therefore, y equals bx, and delta y equals b. And I want you to prove, in a video response, that if y equals bx, then delta y equals b. I will tell you more in a future video, so stay tuned.